All right, students, we are going to look at lesson 14 in Unit 5, and it's using operations on decimals to solve problems. So we're going to start with the second section, and it's called Applying Division with Decimals. It's saying that we're going to divide you up with partners, but obviously we can't do that since you're at home. So let's look at each individual scenario here. Problem A says a piece of rope is 5 7/75 meters in length. If it is cut into 20 equal pieces, how long will each piece be? Well, let's take a look at some division work here. So we have a total length of 5 7/75 meters in rope, and we're dividing that equally into 20 pieces. So 5 7/75 divided by 20. I have no decimal here, so I don't need to move it, so I'm just going to leave it here. My decimal in my quotient will be right here in the same place that it is in the dividend. So 20 goes into 5, obviously 0 times, but 20 into 57 will go 2 times. 2 times 20 is 40. So I'm going to subtract. I get 17, and I bring down my 5. 20 into 175 goes 8 times. 8 times 20 is 160. I subtract, and I get 15. I bring another 0 down. 20 goes into 150 7 times. 7 times 20 is 140. I subtract and get 10. Bring another 0 all the way down. Because remember, it doesn't matter how many zeros we add after the decimal. It doesn't change the value of the dividend up here. 20 goes into 100 5 times, and finally we're done. Ends up equaling 0. So if that length of rope is cut into 20 equal pieces, each piece will be 2,875 10,000ths meters long. So that should be your final answer. And yes, that is how you would say that number. So we have tenths, hundreds, thousandths, 10,000ths. So it's 2,875 10,000ths meters long. Now they're asking us, well, what if we cut that same length of rope into 500ths meters pieces? And how long would each piece be? So again, we have our original length, which is 5 75 meters. And now we're dividing it by 500ths pieces. So I have 2 decimal places in my divisor. I need to move it over. I moved it over twice, so now I'm going to move the dividend decimal over twice, and I will bring it up to my quotient. So now I have 5, because the 0 before doesn't make any difference anymore because I moved the decimal. So 5 goes into 5 one time, and that's 5. And bring the 7 down. 5 goes into 7 one time, and that's 5. Subtract and get 2. Bring my 5 down. 5 goes into 25 5 times. So if I cut 5 7/75 meters length of rope into 500th meter pieces, I am going to get 115 meters. I'm going to get, I'm sorry, not meters. I'm going to get 115 pieces. All right, that's not meters anymore. It's how many pieces will I get. All right, problem B, a tortoise. A tortoise is traveling 945 thousandths miles in 3.5 hours, 3.5 hours. If it moves at a constant speed, how many miles per hour is it traveling? Well, it's traveling 9.945 miles in 3.5 hours. So we're going to divide that by 3.5. So I have a 1 decimal place in my divisor, so I'm going to move it over. That means I have to move 1 decimal place over in my dividend. So I have 35 going into 9, which is 0. 35 into 94 goes twice. 35 times 2 is 70. When I subtract, I get 24, and I bring down the 5. And then I have to say, well, 35 goes into 245. And remember my trick. I'm looking at the last digit, 5, and I have to multiply it by something that's going to end up in 5. Well, 2 times 5 is 10, so that won't work. 3 times 5 will work, but that's not going to be big enough. How about 4? That's going to be a 0. 5 times 5 might be big enough. Let's try it. 35 times 5. I've got 5 times 5 is 25. Carry my 2. That's 15. Oh, that's only 175. So that's not going to work. The next one that will give me 6 is going to end up in a 0, but how about 7? Let's try 35 times 7. 5 times 7 is 35, so I'm going to carry my 3. 3 times 7 is 21, plus 3 is 24. So it is 7. So at that rate, if it moves at a constant rate of speed, it is moving at 27 hundredths miles per hour. Now they're saying, well, at this rate, how long will it take the tortoise to travel 4 and 86 hundredths miles? Well, if we have 4 and 86 hundredths miles and we divide it by the speed, which is 0.27, we're going to find out how many miles it travels in that amount of time. Because the speed times the speed times the time will give us the number of miles that it traveled. So I've got 2 decimals in my divisor, so I'm moving over twice. I'm going to move it over twice in my dividend and bring it up. So now I have 27 into 48, and I know that goes 1 time, so I put that over the 8. Make sure you put it over the 8 so we don't lose our place. And again, this might be helpful to use graph paper. 1 times 27 is 27. When I subtract, I get 21, and I bring down my 6. Again, I need to figure out what times 27 will end up in a 6. What times 7 will give me a number 6 in my answer? The first thing that comes to mind is 8. So if I do 27 times 8, what will I get? 7 times 8 is 56, carry my 5. 2 times 8 is 16, plus 5 is 21, and that would be it. So I've got 18 here. So at this rate, how long will it take the tortoise to travel that many miles? It will take him 18 hours. Poor little tortoise, it just takes him forever to get places. 18 hours to go almost 5 miles. That's a long time. He is walking really slow. So this next section is distance between hurdles. And they said that there are 10 equally spaced hurdles on a track. And these are the hurdles right here. And they're around the track, and they're equally spaced. The first hurdle is 13 and 72 hundredths meters from the start line. The final hurdle is 14 and 2 hundredths meters from the finish line, and the racetrack is 110 meters long. They want us to draw a diagram that shows the hurdles on the track and label the known measurements. And this is always a good thing to do because this is kind of, they're giving you a lot of information. So let's start with the overall track. So I have my overall track, I know, is 110 meters. Then I have 10 hurdles. So let's draw in 10 hurdles. I'm going to start in the middle because that's going to be 5. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hurdles. Okay, so this is the start. This is the finish, and I have 10 hurdles in between. And they gave us more information. They said the first hurdle is 13.72 meters. So in between this one and this one, we have, let's do it this way, we have 13.72. And the last meter, or the final hurdle, is from here to here, and it is 14.02 from the finish line. Okay, so the total from here to here is this 110. And they want to know how far are the hurdles from each other and explain how you know. Well, they said the hurdles are equally spaced aside from this one and this one. So the first thing I want to do is get rid of this amount and this amount to find out how I can divide this up equally. So I'm going to use my space down here to work. I have 110. Let's do it this way, 110, and I need to subtract this 13.72, and this is 110 like this. So I'm going to get rid of that first. I have to borrow from my 1. That makes it 0. That's 10. That makes it 9. That makes this 10. Borrow again, and that makes that 10. So 10 minus 2 is 8. 9 minus 7 is 2. There's my decimal. 9 minus 3 is 6. And again, I'm borrowing. 10 minus 1 is 9. So I have 96.28 once I get rid of this 13.72. Now I need to get rid of the 14.02. So I'm going to subtract 14.02 and get rid of that. 8 minus 2 is 6. 2 minus 0 is 2. I've got my decimal. 6 minus 4 is 2. And 9 minus 8 is 8. So what I know from that 110, I know from the first hurdle all the way to the last hurdle, I have 82.26 meters to work with, okay? We're dividing that equally among these hurdles. Well, how many equal spots do I have? I have 1, whoops, I don't know what happened there. Let me get rid of that. It's kind of funky. I have 1 space here, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 spaces. So it's easy to say, well, I've got 10 hurdles, I'm going to divide by 10. But really, we want to divide that among these 9 spaces. So now I have 82.26. I'm dividing by 9 sections. 9 goes in, I'm going to bring my decimal up. 9 goes into 82 9 times. That's 81. I'm going to subtract, bring down my 2. 9 goes into 12 1 time. That's 9. I'll subtract and bring down my 6. 9 goes into 36 4 times. So the hurdles should be 9 and 1400ths meters apart. This next one is very tricky, so pay attention and please pause that video if you need to think about what I'm saying. You can rewind and listen again, but it's very tricky. A professional runner takes 3 strides between each hurdle. So between this hurdle and this hurdle, that runner is taking 3 strides. But the runner leaves the ground 2.2 meters before. So if the runner's running in this direction, before this hurdle, 2.2 meters, that runner is leaping off the ground. Okay? Then the runner returns to the ground 1 meter after. So over here, there's 1 meter difference over here. And then again, the runner would leave 2.2 meters, okay? So I know in between each of these hurdles, I have this 9.14. So I have 9.14 in between each hurdle. But the runner isn't using all of that space. The runner leaves the ground 2.2 meters before. So let's subtract 2.2 and see what we get. 4 minus nothing is 4. I have to borrow from the 9. That makes it 11 minus 2 is 9, and 8 minus 2 is 6. So the runner leaves 2.2 meters before. That leaves us at 6.94. But then the runner returns to the ground 1 meter after. So I need to subtract another 1. And remember, this is 1 meter, so it goes under the 6. So really, I have 5 94/100 meters to deal with, where that runner is taking 3 strides. So how long is the stride that they're taking? 5.94 divided among 3 equally length strides. Here is my decimal. 3 goes into 5 one time, and that's 3. I subtract and get 2, bring down my 9. 3 goes into 29 9 times, and that's 27. I subtract and get 2, bring down my 4. 3 goes into 24 8 times. So how long are the runner's strides between hurdles? They are 1 98/800 meters long. And that is how it says, show your reasoning. I just showed you all of my work. We started with the distance between the hurdles. We subtracted the amount that he or she jumps and doesn't use for stride purposes, which is 2.2 before and 1 meter after. We got 5 94/100, and that's the number where the runner is actually running in between the hurdles. And we divided that by 3 and got 1.98. Told you it was a tricky one. So let's move on to talking about tennis courts. This is another problem where it's very important to look at what they're talking about and draw diagrams and make notes. So don't be afraid to draw all over your book. We're not going to do all of these. We're only going to do the first 2 on this one. So you can cross off number 3 on your workbook. So on this one, the full tennis court used for doubles is a rectangle. So here's the full tennis court, and it's a rectangle. We can kind of see that it's a rectangle. All of the angles made by the line segments in the diagrams are right angles. So they're saying that this is a right angle, this is a right angle. Okay, so they're giving you information to tell you it's not skewed, even though it looks like it's skewed because of the depth of the court. The net partitions the tennis court into 2 halves. So here's the tennis court, the net. So one team plays on this side, one team plays on this side. And they're saying it partitions this whole court in half. And they want to know, is each half a square? And explain your reasoning. Well, we know the length of the width of the tennis court because they gave it to us in these sections. So we need to find out what is the width from here to here. And we can find that out by adding 8.23 plus 1.37 plus 1.37. So let's do that. So I have 8.23, 1.37, 1.37, and I'm going to add them all up. 3 plus 7 is 10, plus 7 is 17. Carry my 1. 1 plus 2 is 3, plus 3 is 6, plus 3 is 9. Here's my decimal point. 8 plus 1 is 9, plus 1 is 10. So I know the length between here and the side is 10.97. So here is my length. You guys might be a little better with your straight lines, but from one edge to the other is 10.97. And they want to know, did they split this court directly in half with the, I'm sorry, when they split this in half, does it make a square? Well, the rule for a square is all sides have to be equal. So we know this side is 10.97. So now we got to figure out the length of this side from the net to here. Well, we know the entire length of the court is 23.77, and they said they split it in half. So 23.77 divided by 2 is going to give us the measurement of the half of the court from here to here and from here to here. So 2 goes into 2 one time, 2 goes into 3 one time. There's 1 left over. Here's my decimal point. 2 goes into 17 8 times, and there's 1 left over. 2 goes into 17 8 times, and there's 1 left over, and 2 goes into 10 5 times. So what we just found out is from here to here is 11 and 885 thousandths, and from here to here is 11 and 885 thousandths. So this number would have to equal this number in order for this section to be a square. So when it's cut in half, is each half a square? No. And the reasoning is the sides are not, that's a D, the sides are not equal lengths. And they can look at our math to see that we did that correctly. Then they want to know, is the service line halfway between the net and the baseline, and explain your reasoning. Well, they showed us the service line here. And the service line is from the net here is 6.4. And they want to know, is it halfway from the net to the baseline? Well, we know the length from the net to the baseline is 11.85. 11.885 minus that 6.4. And if it's halfway, we should get 6.4. So let's take a look, and we'll get 5 minus nothing is 5, 8 minus nothing is 8, 8 minus 4 is 4, and 11 minus 6 is 5. So what they're saying is from here to here is 6.4, but from here to here is 5.485. So is the service line halfway between the net and this baseline? Again, the answer is no, and explain your reasoning. From the net to the service line, it is 6.4, and from the service line to the baseline, it is 5.485. So those are not equal lengths, so it is not halfway. And like I said, we're going to skip number 3 for this video purpose. Whoops, cancel that out. Let me do this. And we're on to our summary. And basically, the whole purpose of this lesson is to use diagrams. They're letting us know that drawing diagrams, using diagrams is going to help us see exactly what we're talking about in our mathematical situation. We used the hurdles and we drew that diagram out. And once we did, it was easy to see that we didn't need to divide by 10, we needed to divide by 9. The tennis court was another great example, showing the whole court and what the baseline is and the service line is, and seeing the net being splitting up the court. So the importance of this whole lesson is when you get a word problem like this, or a scenario that they're telling you about, the best thing you can do if you don't understand what they're talking about is draw the diagram. They will give you enough information to sketch out something. And you saw my diagram of the hurdles. It wasn't anything fancy, but it let us know what they were talking about and how we could add the different numbers, label the different parts, and figure out from there what they were talking about. So that's our lesson for today. We're going to do practice problems in class, and I hope you have a great weekend.